Hello, good afternoon. ලහිරු රන්මිනී දෙන්නම ඉන්නව නේද? Hello, ලහිරු මාව ඇහෙනවද?
ඔව් සර් ඇහෙනවා.
Okay, රන්මිනී. Okay, right. Let's start the lecture because it's already 2:15. So it's better if we start the lecture. Right. So today I am targeting to cover some of the important topics with you. So before that, I need to give you a kind of a reminding session which we discussed last time. So so I think it's better if I give you this reminding session because today's session is also interrelated with this session. So it's better we have a few minutes on the things we discussed on last time. So hope you all can remember that we discussed about the stress distribution in soil. So we say stresses are generated due to the self-weight of soil, and the other thing is we discuss that due to the external structures also the stresses are uh, creating. So the distribution of the stresses due to these external structures we discuss in various theories. So we first discussed that the approximate method can be used to evaluate the stress distribution within the soil due to external structures, right? So we say 2-to-1 stress distribution is there so that we can evaluate the stress distribution at any point be, below the external structure. So we discuss about that thing. Then we moved to very important topic, that was the bosonics theory. So hope you all can remember, right? So this is the approximate method. There we discussed that due to the external structures, the stress distribution can be evaluated using this theory, that is 2-to-1 method, or we can say approximate method. So using this method, we can evaluate the stress at any given point below the external structure, so that we have to use this 2-to-1 method and evaluate this one. Actually, what we said was the results coming from this theory can be still used in our civil engineering applications, but it is more the safety factor of the result is high. So it is more safe, means our designs will be more conservative. The structures will be more large, more big if we use this theory. So whatever the soil improvements, whatever the conclusions made, it will be more conservative in case if we use 2-to-1 method. So then we discuss about one of the major important theory, that is the bosonics theory. So bosonics theory, we discuss, and uh, we have studied that the theory has been derived for point loads. So so this is the equation for point load. So and then it has been further developed for the line loads and for the rectangular area loads and circular area loads. So we discuss about these things, right? So and we discuss about few examples for rectangular area and circular area as well. So what I said last week, we will discuss about some of the examples for rectangular area, and then you will get the exact understanding on this theory and how it can be applied to evaluate the stress distribution below a rectangular loaded area, right? So today we will discuss about some of the practical problems so that you can get used to this theory, and during your exam this area definitely it will be assessed, so you should have to have proper understanding on this theory. Okay, so We discussed that this is one of the example we did. So if we are going to use this graph to evaluate the rectangular area loading, so in that situation, you have to understand this rectangular loaded area has been derived with this graph. So if you are going to use this graph, the condition is your point of interest. Now this is the point of interest that you are looking for, right? So this point of interest should coincide with one of the corner of this rectangular loaded area. So this is one of the corners, right? So you can see my mouse pointer. So this is one of the corners, right? So this is one of the corners, and then this is the point we are interested in. So it is coinciding with each other. So that's the condition. The rectangular loaded area should be there. And also the rectangular loaded area, there are four corners now. One of the corners should coincide with the point of interest, right? So that is the condition. So with that condition, we say, okay, this is the rectangular loaded area. So, and then because of this rectangular loaded area, if we are going to use the graph to evaluate the vertical stress increment under given point, in that situation, that point should coincide with the corner of a rectangular loaded area. That's the condition. But in this situation, the R point is our point of interest. So this is the area that we are interested in. This is the rectangular loaded area. So this rectangular loaded area, this point of interest is not at the corner of the rectangular loaded area. So that is a problem. So we cannot directly use our graph in this situation because the graph has been derived for some other condition, right? So the condition is the graph condition. What is that? A corner of the loaded rectangular area should be coinciding with the point of interest. Now our point of interest is here. The four corners of the loaded area, this is one corner, this is another, this is the other, this is the final corner. So this point of interest is not coinciding with any of the corners, right? So as a result, what you have to do is you have to make sure that you divide this area, that you make necessary arrangements for this area to have one corner. Sorry, Sandamali, can you mute yourself? Sandamali, okay, right, right. So our next target is to have a corner of this loaded area where it coincides with R point, right? So that's what we did here. So we divided this loaded area into two so that this loaded area, this dark blue color one, that loaded area, the corner here, it is coinciding with the point of interest here. Okay. And the light blue color, the corner of this loaded area is coinciding with this corner. So that for this small rectangle, there are two similar rectangles here. So for each one, you can use the graph because the loaded point is coinciding with the point of interest here, right? So with that understanding, we have used this theory. So in the situation, your point of interest here is, so your first check should be whether it is coinciding with the corners of the loaded area. Now this is your point of interest. මේක තමයි ඔයා බලාපොරොත්තු වෙන point එක. ඔයා graph එක පාවිච්චි කරන්න නම් තියෙන ඕන අවශ්‍යතාවය තමයි graph එකේදී අපේ loading area එක අපේ දැන් ඔය external load apply වෙන area එකේ එක corner එකක් මොකද්ද වෙන්න ඕනේ? අපි සලකනු ලබන පොයින්ට් එකත් එක්ක සමපාත වෙන්න ඕන. The loaded area, there are four corners in case of rectangle. So in that situation, one of the corners should coincide with the point of interest. But this is the loaded area. Okay. So the corners are, this is the first corner, second corner, third corner, and the fourth corner. Okay. But your point of interest in the second case is here, which is not coinciding with any of the corners. So that what you have to do is now, you have to divide this loaded area in a way that the corner of the divided area should coincide with this point S. So how to do that? So this is the way, right? So we divided the area into two, where one of the corners coincide with the point of interest here. Okay, so this dark blue color rectangle, one of the corner is here. That corner is coinciding with point S. So light blue color, one of the corners here, which is coinciding with point S. So our requirement is satisfactory. So what we do is, for this small rectangle, we will apply this graph, right? And multiply by 2, because the dimensions of each rectangle is correct, is same, right? So it is similar. So dimensions of each rectangle is similar, so that this m value, n value is similar. So if you know the m value, n value, you can use this graph. N value is the horizontal axis, and this curved line will be the m. So you get the point of intersection and go horizontally until you find the corresponding value of I. Okay. So if you know the I value, if you know the surface external load per unit area, you multiply this value by this I value, corresponding I value, so that you can get the stress at this point. Okay. Clear? තේරුණාද ළමයි? තේරුණ නැත්නම් අහන්න. මොකද අපි ගණන් වලට යන්නේ මොනවා හරි ප්‍රශ්නයක් තියෙනවා නම් දැන් අහන්න. Is it clear, Asha? Lahiru, these are the things we discussed last time. So I thought to give you a reminder, because today we are going to have a kind of Samarajiva, can you mute yourself? Samarajiva, can you mute yourself? Samarajiva, please mute yourself. Mute කරගන්න පුළුවන්ද?
මම දන්නේ නැහැ මේ මිනිහා ගණන් කියන්නේ අපි දන්නේ.
Okay, right. So I hope everybody is clear with this explanation. So I
Sir,
think it's better. Yes.
sir, M equal to B over Z value, sir. Z value කොහොමද?
This add value is the depth. Let's say this is the point you are interested. In each of our question, Asha, you have been given with Z. So what is given is a rectangular footing area, footing with load intensity of 20 kilonewton per square meter is shown. Find sigma Z at 2.5 meter depth for point, right? 2.5 meter. It is the Z value, right? So
Okay,
in this
sir.
situation, for point R, so you have divided this area into two. So our requirement is satisfied, because this small rectangle, one of the corners coincide with this point of interest. Now our requirement is okay. So what you have to do is, you will have to get this dimension of this small rectangle. The length is 200, width is 150. So What is M? What is N? M is B over Z. And then N is L over Z. So now capital L is the length. So in that situation, so this is small rectangle, what is L? 200 centimeter means 2 meter. So L is 2, Z means here depth 2.5. So that L2 divided by 2.5. That's what here. See, L2 width is 1.5 and Z is 2.5, that is the depth. So B of Z is 1.5 divided by Z 2.5. L is 2, Z is 2.5, so 2 divided by 2.5. So if you know M value, if you know N value, you have to refer to the graph so that you can find the I value. Okay. So if you know N value, here N, if you know the corresponding M value, so if you once you get the simple N value, you can go up until you find the corresponding M value. So once it is intersected, you go horizontally, then you can find the corresponding I value. Okay. So that's what we did here. I value is 0.125. So applied load is 20. 20 into 0.125, that is the delta sigma Z of this small rectangle. Okay. Of this small rectangle. Because the dimensions 2 meter and 1.5 meter is this small rectangle. Okay. So, but here the similar dimension is available for this rectangle as well. So, you have to repeat the process once again, right? 2 meter, 1.5 meter, then depth is 2.5 meter. You have to calculate simple M value. You have to calculate simple N value. Then the similar thing, no, I value. So that's why without going for another step, what I did was you calculate the delta sigma Z value for one rectangle and multiply by 2. Okay. So that the final value 5 kilonewton per square meter. So what this mean? The meaning of this is, so the contact pressure from the footing is 20 kilonewtons per square meter, right? At the given point R, below 2.5 meter depth, the stress has been reduced to 5 kilonewton per square meter. Understood? The surface pressure is 20, but when you go down, it has been reduced to 5 kilonewton per square meter. That's the physical meaning of it. Okay. Clear, Asha?
Yeah, sir. Sir, then I value is if I identify I value to use the graph.
Yeah. So let me show you. Now M is 0.6. Okay. N is 0.8. Let's go to the graph. N is 0.8, no? So now this is 0.1, 0.2, 0.3, 4, 5, 6, 7, 8. So this is 0.8. Okay. So now this Hello? Understood?
Yeah, sir. Then total sigma that is may multiply by two.
Ah,
If two
okay.
rectangles,
Yes. Actually, I think my voice is not heard by you because I think I have been muted. Sorry. So I will repeat here. So now simple n value you know how to calculate. Okay. Simple n value you know how to calculate and mark here in the graph, and simple m value you know how to calculate and mark here in the curve line, and then finally you can get the corresponding I value. Okay. So when you move to the next slide, you can see now how to calculate the simple n value, and obtain I value from the graph. And then sigma Z is the surface contact pressure, which is given in the question, multiplied by this I value. Okay. So, but the problem is you have calculated this I value for these dimensions. I is calculated for L is 2.0, B is 1.5. What is that? This is for this small rectangle. See, the dimension length is 2 meter, width is 1.5 meter. So what you have calculated the influence. I is the influence value. The influence has been calculated for a small rectangle. So the same procedure you have to repeat for this rectangle as well, because entire area has been loaded now. So when you check the dimensions of this light blue color rectangle is similar as this dark blue color rectangle. Okay. So that's why you multiply by 2 here. So similar thing you have to repeat otherwise. So that's why you have to multiply by 2. So in case you don't have a rectangle, another rectangle over here, you don't need to multiply. Okay. So our main reason to divide these rectangles is you have to use this graph in case one of these corners of the loaded area should coincide with the point of interest. But here, our point of interest is here, but the corners of the rectangle area are not coinciding with the point of interest. That's why we divided these two rectangles at this point. Okay. Asha තේරුණාද?
sir,
ඉසුරු
if then rectangle then අපිට දැන් අපි divide කරනවානේ sir දෙකට දැන් 3 තිබ්බොත් ඒක 3ෙන් වැඩි කරන්න ඕනේ නැද්ද? නිකම්ම දැම්මොත් totalද?
නෑ නෑ. ඔයා මෙතන ආශා right? පොඩ්ඩක් ඉන්න. මේ බලන්න. අපේ මේ rectangle loaded area එකේ අපි අනිවාර්යයෙන්ම සලකන්න ඕනේ අපේ loaded area එකේ එක කෝණ එකක් coincide වෙන්න ඕනේ අපේ point of interest එක්ක. දැන් මෙතෙන්දී ඔයා මේක පොඩියට බෙදුවනේ. පොඩියට බෙදපු නිසා තමයි ඔයාගේ ඒ influence value එක ආවේ මෙන්න මේ පොඩි area එකකට විතරයි. ඔයා මේක සම්පූර්ණ area එක ඔයාට මේ වෙලාවේ ගන්න බෑ. මොකද point of interest කෝණ එකක් එක්ක සම්පාත වෙන්නේ නැහැ. ඒ හින්දා තමයි ඔයා මේක දෙකකට බෙදුවේ. හිතන්න ඔයා තුනකට බෙදුවා නම් තුනකට බෙදුවා නම් මොකෝ වෙන්නේ? ඒ තුනෙන් වැඩි කරන්න ඕන. හතරකට බෙදුවා නම් ඒ හතරෙන් වැඩි කරන්න ඕන. පහකට බෙදුවොත් ඒ පහෙන් වැඩි කරන්න ඕන. සමාන නම් විතරයි. නැත්තම් හැම රෙක්ටැන්ගල් එකට වෙන වෙනම කැල්කියුලේට් කරන්න ඕන. දිගයි පල්ලයි සමාන නම් විතරයි ඔය හතරෙන් වැඩි කරන ඒවා, පහෙන් වැඩි කරන ඒවා, තුනෙන් වැඩි කරන ඒවා කරන්න පුළුවන්. දැන් මම තව එක්සැම්පල් එකක් ඕගලන්ට පෙන්නන්නම්. මේ බලන්න. දැන් මෙතෙන්දී okay. Now your point of interest is point T. Your loaded area is somewhere here, which is inside. Your point of interest is outside the loaded area. Okay. So this is the plan area. In the plan area, only this area is the loaded area. Okay. Now you have been asked to calculate the vertical stress increment somewhere which is outside the loaded area. Okay. So in that situation, how to divide? Huh? Then you have to think. So this is the way I will show you. So first rectangle, you mark like this. Second rectangle, you mark like this. Now you may wonder why this area is more than the loaded area. Okay. You understand? දැන් ඔයගලන්ට ප්‍රශ්නයක් වෙන්න ඕනේ ඇයි මෙච්චර මේක බෙදුවේ? මොකද මෙන්න මේ ඒරියා එක ගත්තාම මේ ඒරියා එක වැඩිපුර ඒරියා එක. අපි මෙහෙම කන්සිඩර් කරන්න අවශ්‍ය නැහැ. But what I did was I make a rectangle like this and again another rectangle like this so that my requirement is satisfactory. What is my requirement? One of the corners should coincide with the point of interest so that I can use the graph. මට graph එක පාවිච්චි කරන්න තියෙන අවශ්‍යතාවය හින්දා තමයි මම මේක දෙකකට බෙදන්නේ. Okay. So now I have additionally considered this area now. So what I have to do now is I have to deduct this area. So how to do? This is the uh, additional area which I considered. This is another additional area which I considered. Okay. So now what I have to do is these rectangles also should be drawn in a way that one of the corners coincide with this point T. Then only you can use the graph. Okay. So you cannot get some entire additional rectangle once and then deduct. You cannot do that. What you have to do is, even for deduction, you have to select the rectangle in a way that one of the corners coincide with the point of interest. Then only you can use. Okay. So now another point due. So it is also outside the loaded area. Loaded area is only this area, no? So this is the loaded area. Okay. So point U is somewhere outside. So how to do? We have to consider this big rectangle. One of the corners of this big rectangle is coinciding with the point of interest. So you simply apply uh, simple n value, simple m value and use the graph and evaluate. Is your answer correct? No. Why? Actual loaded area is smaller than this area. So if you give the answer like that, then you have increased the loaded area, which is not the actual situation. Okay. So what you have to do now is you have to deduct the additionally considered area. But for the deduction also, the selected deducted rectangle, one of the corner should coincide with this point U. Okay. The point U, which is the desired point here. So this point U should coincide with the deductible rectangle area as well. How to do that? You see. So I deduct this rectangle, green color rectangle I deduct. Again I deduct this rectangle as well. Right? So that this will be the resultant. Okay. My requirement now satisfactory. Before that, before very first thing, I draw a big rectangle. So the corner is coinciding here. So now I know I have considered certain additional area. So now I am going to deduct that additional area. But I have to think how to draw the deductible rectangle because a corner of the rectangle should coincide with the point of interest. So I decided, okay, this rectangle, one of the corners coinciding with point U. Again, I draw this rectangle, that rectangle also, one of the corners coinciding with point U. Okay. Now, what you have to do is, first you have to evaluate simple m and simple n value for this one and check the graph for I value, multiply by sigma so that you can calculate the sigma z. And then you have to evaluate for this is a small green color rectangle. Check for simple length, check for simple length. Go to the graph and find I value, and then multiply by sigma surface contact pressure, so that you can evaluate the vertical stress at this point. So then you have to calculate for this orange color one. So that is also possible. Now what is the mistake now? Can somebody tell me? Is there any mistake? Huh? There's a mistake. What's the mistake? We have deducted this area 2 times. අපි දෙපාරක් මේ ඒරියා එක අඩු කරා. කොහොමද? මේ green color area එක අඩු කරනකොටත් නිල් පාට එකෙන් මේ කෑල්ල අඩු කරා. orange color area එක deduct කරනකොටත් මේ color එකේ මේ කොටස වැඩිපුර අපි අයින් කරා. දැන් මේක දෙපාරක් අයින් වෙලා. දැන් එහෙමයි කියලා ඔයාට මෙහෙම තියෙද්දි ඉතිරි rectangle එක මේ කෑල්ල විතරක් අඩු කළා දාන්න බෑ. ඇයි? හේතුව මේක එක කෝණ එකක්වත් මේ point u එකත් එක්ක සම්බන්ධ වෙන්නේ නැහැ. තේරුණාද? ඒ අපේ requirement එක මොකද්ද? graph එක පාවිච්චි කිරීමේ requirement එකත් එක්ක මේක satisfy වෙන්නේ නැහැ. ඒ නිසා තමයි මම additional area එකක් විදිහට මේ කෑල්ල deduct කරේ. එතකොට තමයි මේ point u එකත් එක්ක coincide වෙන්නේ. Okay. Now I made a mistake. What is the mistake? I have deducted this area 2 times, so that this area I have to add once, right? I have to evaluate simple m and simple n value for this area, and then check for I value, get the sigma value, so that you can decide how to do. Okay. So let's move today some of the practical examples. Right. Right. A plan of a footing carries a uniform pressure of 160 kilonewton per square meter on the surface of soil as shown in the figure. Find the vertical stress increment due to the footing at a depth of 4 meter below point C. Okay. These kind of practical problems can be there in your exam paper, right? We will say, okay, footing is there. At this point C, you have to evaluate what is the vertical stress increment. And I may say, okay, at this point C, there's a kind of manhole. So as a result of this footing construction, will there any impact if the cover slab bearing pressure is this value? Something like that, I can make a big problem in your exam paper. මොකද්ද කියන්නේ? 14 area 14 එකක් තියෙනවා. 14 එක නිසා මේක load වෙනවා. ඔයාගෙන් අහනවා මෙන්න මෙතන මීටර දෙකක් පල්ලෙහෙන් තියෙනවා cover slab දාපු manhole එකක් එළියට පේන්නේ නැහැ. ground එකට පේන්නේ නැහැ. මේ 14 එක හැදුවොත් මේ cover slab එකටයි manhole එකටයි ප්‍රශ්නයක් වෙයිද? මෙයාගේ capacity එක මෙච්චරයි. එතකොට දැන් මේ වෙනකොට තියෙන බර හිතන්නකො මෙයාගේ capacity එක 100යි. දැන් මේ වෙනකොට මේකට 75ක load එකක් ඇවිල්ලා තියෙනවා. මේක දැනට safe. නමුත් ඔයාගේ මේ 14 එක හැදුවොත් මේකට ප්‍රශ්නයක් ඒවිද? ඔන්න ඔයාගෙන් අහන ප්‍රශ්න. So you have to answer for that kind of questions, right? So simple problem. Now you may wonder this irregular shape footing, how to evaluate? This is not a rectangle. This is not a circle. How to do now? That may be your problem. So this kind of irregular shapes, you have to think how to deviate these areas, how to derive these areas, irregular areas in shapes you know. Now you know some of the shapes, circles, rectangles, likewise, right? So how to make necessary arrangements of these irregular areas so that you can evaluate these irregular areas with the known shapes. Okay, right? So now I will discuss with you how to make the rectangles for your information. Okay. I'm not going to calculate simple m value, simple n value, and I value, and sigma z value. I am not going to calculate. Okay. So I will give you 2-3 minutes because I have many things to cover today. I will give you only 2-3 minutes. Try to work by your end and evaluate the arrangement of rectangles. Then we will discuss together. I think that would be the best way. So I will give you 2-3 minutes. Get a piece of paper and work on this and try to do the rectangle arrangement. Remember, when you select the rectangle, the corners of the rectangle should coincide with the point of interest, that is point C. So ඔගොල්ලෝ rectangles select කරනකොට තියෙන requirement එක තමයි ඒ සියලුම rectangle වල කෝණ එකක් point C එකත් එක්ක coincide වෙන්න ඕනේ. Okay, so I will give you 2-3 minutes. Try to work on this and evaluate how to prepare with the rectangles, right? Okay, how about you? Asha, did you try? Lahiru, Pranmini, Samarajiva, Sandamali, did anyone try? Hmm? Nobody? ආශා තේරුණාද? ආශා ඕගලන්ට rectangles ටික අඳගන්න පුළුවන්ද?
Yes, sir.
කරාද?
No photo ගවන්න sir.
right. මට chat history එක දාන්න පුළුවන් නම් chat එක. Lahiru, Ranmini, if you complete, please share your screens with oh, piece of papers with the chat box. Samarajiva Sandamali. Now, Asha, there's a problem, no? Now, um, you have selected one of two rectangles over here. Okay. So, first rectangle, it is not coinciding with the point C. You see? So, what I am saying, the checked one, the checked rectangle. So, that checked rectangle, it is not coinciding with point C. Only the upper rectangle is coinciding with point C. That may be a problem. Because you cannot go for the graph and evaluate I value in case your point of interest is not coinciding with the rectangle area. Okay. So now let me explain. Right. So this is the requirement. Once you divided for, or once you refer to the rectangular loaded area, and if you are going to use this graph, so the requirement is this point of interest should coincide with the loaded area, one of the corners. So there are four corners in the loaded area. No, this is one corner, this is another corner, this is another corner, and this is the last corner. You see, the last corner, directly below that only you are considering the vertical stress. That is the requirement to use this graph. Okay. So now in this situation, how to divide? So let me use this point. This is my point of interest. Okay. So my requirement now is I have to draw the rectangle so that one of the corners should coincide with this point. Okay. So this is one of the rectangle I am using. Okay. So my requirement is now satisfactory because there are four corners in this big rectangle, right? So that this point is coinciding with point C. Okay. So I can use the graph. What to do now? So simple M value is the L, simple M is B over Z, and then simple L value is, simple N value is L over Z, right? So simple M is B over Z and simple N is L over Z. So L is here 12 and Z value is the depth. What is the depth? 4 meters below. So 12 divided by 4, that would be 3. Okay. And in this rectangle, simple B over Z, that would be B, simple M value. Simple M value is 2 plus 2, that is 4. 4 divided by 4, M is 1. Right? Okay. Now, simple N is L divided by Z.
Excuse me, sir.
Right? So, L is 12. Depth is 4. So, 12 divided by 4, that would be 3. Okay. And simple M, 2 plus 2, it is 4. 4 divided by 4. That is 1. So if you know simple n value and simple m value, simply you can use it at the graph. Okay. Now here simple n value we got it as 3. Simple m value we got it as 1. So you go up, 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 up until you find the corresponding simple m value, right? So now you know the simple m value 1, simple n value 3. So once you get the point of intersection, you go horizontally until you find the corresponding I value. I value is somewhere here. So this is 0 0.2, this is 0 0.21, this is 0 0.22. So that, yes, I received several messages. Asha, B is 12. I didn't get your message, Asha.
B equal to 12 and N equal to 4 is it wrong?
This one, no? Is that this example? Asha, what you are referring to this example, right? So now forget about the workings that you have done. So now I am going to tell you how to do this one. Now here, simple m value is b over z. Simple n value is l over z. So now here, I have drawn the rectangle like this. So simple n value is l over z, no, length. Length is 12, depth is 4. So the simple n value is 3. Simple m is here we have 2 plus 2, that is 4. 4 divided by 4, that is 1. Right? So you go to the graph. Simple m value is 3. Simple n value is 1. And then I value is 0 0.202. Let's say like that. So the I value is 0 0.202. Okay. 0 0.202. Okay. Now your sigma value here 160 kilonewton per meter squared. So now what you have to do is sigma value is equal to I into contact pressure, sigma naught. Actually, last week we discussed about this one. So I value is 0 0.202 into 160, right? So you get the final answer. Let's say answer is capital A, sigma 1, right? Okay. Then you move to this one, right? So now from this rectangle, I know this area and this area I have additionally considered. Now I have to think how to deduct this area. I cannot simply deduct this area, calculate M and N, this area, calculate M and N. I cannot do because this area I can simply deduct because the reason it is coinciding with this point. But this area, it is not coinciding with the point of interest point C. So that it is not possible to deduct this area alone. So that's why I considered this area. So I consider this brown colored area. Now I calculate simple m and simple n value for this brown color one, repeating the same procedure. So simple n value 12 divided by 4, and then simple n value 2 divided by 4. So you go to the graph and evaluate the I value, multiply by 160, and you evaluate the stress due to this one, this brown color one. So if you know the stress of this blue color, and if you know the stress of this brown color, so what you have to do is the stress coming from this value, let's say A, capital A, and stress coming from this brown color one, let's say it is B. So you have to A minus B. You have to calculate A minus B so that you can have the stress due to this checked area at point C. Okay, I am repeating. So due to the blue color area, you know the stress at point C is A, capital A. Due to the brown color area, stress due to this brown color area at point C is capital B. So you have to deduct A minus B so that you can have the stress due to this checked area, the colored area at point C. Okay. Now what you have to do, evaluate balance area is this one. So this balance area, now you have to think how to evaluate. It can be done by assuming this rectangle, then evaluate simple m and simple n value. Simple m is 4 plus 4, that would be 8 divided by the depth. So that simple n can be calculated. Simple m value is 2 divided by 4. So that will be 0.5. You go to the graph so that this area you can calculate. But the problem is you have additionally considered this area. So that area you have to deduct. So I mark that area in gray color. So this is the final outcome. First you had blue color one, right? From that blue color one, let's say your answer is delta sigma z. That is this blue color one. So you get the answer A. Then you deducted the top part, this one, this brown color one. So that brown color one, you get answer B. And then you have the top part, this one. So this part, you evaluate delta sigma z, that would be the answer C. So finally, you deducted this area, the ash color one. So that ash color one will be this one. So the answer will be capital D. So the final delta sigma z value is of this shape, right? This shape will be A minus B plus C minus D. Okay. Is that clear? Asha, is there any problem now?
No, sir.
It's clear, right? So if you have any problem, please let me know. Udeshika, Ranmini, Samarajiva, Sandamali, if you have any problem, please let me know. The reason I am going to put one question from this area. The full question will be there in your exam paper, right? So maybe 25 marks you can get if you know this area well, right? Okay. So with that, we will move to another example, this one, right? Find the increase in stress under 3 meters from point A in the following figure with Q 200 kilonewtons per square meter using charts in calculation of stresses. Right? Your point of interest is here. Okay. So this area, right? This is a area load. This area is not a standard shape. It is not a rectangle. It is not a circle. It's a kind of irregular shape, right? But you can see that this area can be evaluated with rectangles, right? So our main requirement is when you divide the rectangles, one of the corners should coincide with point A, right? So that is the requirement. So how to do? This is very easy, no? So we will evaluate the rectangles like this, right? So we have blue color one, orange color one, and red color one, right? So let's say the red color one length is 2 meter. Sorry, actually it is wrong. This one here it should be 4 and here it should be 2. Okay. So length is 4 meters, width is 2 meters. Why? Blue color one, no? Here the length is altogether it is 7. This part is 3. So that here to here it is 4 meters. Right? Width is 2 meters. So length is 2 meters. Length is 4 meters. Width is 2 meters. Depth is 3 meters. So B of Z can be calculated. 2 divided by 3, it is 0.67. Right? And then length divided by Z, it is 4 divided by 3, 1.33. So you go to the graph. If you know the n value as 1.33 and m value as 0.67, so that you can go to this graph and evaluate the corresponding I value. I multiplied by the surface contact pressure, that is 200. So I multiplied by 200, that would be the answer A, right? And the other one, this area, what is the dimension? Length is 3 meter, width is 2 meter, 3, 2, depth is again 3 meter. So evaluate M value, N value, and I value to evaluate the final B value. And then we have another area, that is red colored area. So when it comes to the red colored area, length is 4 meter, width is 3 meter, right? Length is 4 meter, width is 3 meter, so that you can evaluate M value, N value, and then I value. Finally, you can evaluate C, right? I don't have much time. That's why I mark A, B, C. So when you have time, I will upload this presentation in your Moodle so that you can refer to this presentation and evaluate these stresses by yourself. So uh, when we meet next week, you come with some questions if you have any doubts, right? So that we can discuss those things during the lecture, right? So if you know the ABC value, so how to combine now? No need to deduct. So if you add this area and this area, then you can combine the total area, right? You can have the combined total area. So for the stresses also, what you have to do is you have to add A plus B plus C. Then you can find the final sigma Z value. There's no multiplication, there's no deduction, only the addition. All the things will depend on how you divide, how you draw your rectangles. Okay, understood. Is it clear, Udeshika,
Yes,
Asha?
sir.
Clear, no? Right. Okay. Let's move to the other example. This kind of question was there in your previous batch exam paper. So for the figure, calculate the differential in stresses, means stress increment due to shown foundation under point 1, 2, and 3. 1, 2, and 3. So there are 3 points given. So you have to calculate for every 3 points. Knowing that the required depth is 2 meter and the surface loading is 200 kilopascal. So everything is given. So let's consider the point number 1, right? When you consider point number 1, so you have to decide how to evaluate the rectangles, right? So let's try. So this is the rectangle arrangement. Blue color one, definitely we have go for, right? This blue color rectangle, definitely without the issue, we can go for. And then I draw another big rectangle, yellow color one, right? So what I have done is, I made my logic where a point of interest is coinciding with the corner. But additionally, I have considered this area. Now I have to think how to deduct this area. Okay. So how to deduct? So I will consider a rectangle like this, a big rectangle, and I will deduct. Let's move to the other slide. So I deduct. I need to remove this area. Okay. So how to do? I deducted this rectangle. You see? So there was a rectangle. This yellow color rectangle was there. So I evaluated simple m and simple n value. Kamarajiva, I muted you. Okay. So let me erase. Okay. Now the blue color rectangle I considered and yellow color rectangle I considered, but this dotted area I have additionally considered. So now I'm going to deduct this area, but I cannot simply do. I cannot simply deduct this dotted area because that dotted area, one of the points are not coinciding with the point of interest. Okay. So because of that thing, I need to deduct a rectangle where a corner is coinciding with the point of interest. Okay. So that's why I deducted this area, the entire area I deduct, so that this point of interest will be coinciding with each other. Now what happens? The result will be, now we receive this area and this area. Okay. Because we deducted now this area. So that means we receive this area and this area only. Now it is very easy now. This area we can additionally consider because it is coinciding, that one of the corners is coinciding with the point of interest. So this area I have additionally considered the ash colored one. So now the evaluation, it is like this. So first we considered the blue color one, right? Blue color one. Length is 7 meter, width is 1 meter, right? Length is 7 meter, width is 1 meter, depth is 2 meter. So you can evaluate m value, n value, and I value. Let's say the sigma z value is a. And I have additionally considered this yellow color area, right? So that area also, you know what is the dimension, right? Here it is 1 meter, means from here to here it is 5 meters. And from here to here it is 7 meter. Length is 7 meter, width is 5 meter. So length is 7 meter, width is 5 meter, depth is 2 meter. So that m and n can be calculated. I value can be evaluated so that sigma z can be evaluated. So now we have this area. So this area we have to deduct. So anyway, now the dimensions are, here we have 4 meter, here we have 5 meter, width is 4 meter, length is 5 meter, depth is 2 meter. You evaluate the n value so that I value can be found. And then additionally you consider this ash color area. So that ash color area, simple L, simple B and Z values are given so that you can evaluate the I value. The finally, once you receive this A, B, C, D values, how to get the final delta sigma Z? This blue color one definitely should be there. And then you add with the yellow color one. But you have to deduct this area in order to omit the additionally considered area. And finally, you have to add this rectangle area. This is how you have to find the final delta sigma Z for this situation. Is it clear? Asha, clear? Ranmini,
Yeah, sir.
clear. Ranmini, how about the others? Sandamali, Vijayakon? Huh? Everybody
Yes,
should,
sir.
it's clear, no? Okay, right? I will show you one of the examples which I gave for your previous batch so that you can understand to which extent I am expecting your knowledge. Okay. At the end of this session, I will show you an exam paper. Okay. Right. So considering the point number 2, now you have to decide how to evaluate your rectangle arrangement. Right. So I will consider like this, blue color rectangle. And then this orange color rectangle, I will consider up to the point here. Now, point number 2 is our point of interest, no? So because of that thing, every rectangle should coincide with this corner, right? Okay. So I consider first rectangle like this. This is my first rectangle, blue color one. Then I created another rectangle in this orange color up to here. And I created another rectangle like this, right? So every rectangle which you consider should coincide with point number 2. That is the requirement. Another rectangle I will create like this, right? So now the problem is I have not considered this area and I have additionally considered this area twice. When I consider this orange color, we have considered this small area, right? When we consider this green color area, this area is also counted once again. So that means the area here and here, it is similar. Okay. I don't need to consider this area additionally. The reason, the similar area I have counted here twice. So that even though you deduct this area and add this area, it is similar, right? You can do like that. You can deduct this area and again you can add this area. No point, no? It is same. So because of that thing, I will not consider this area because I have considered this area for 2 times. Okay. So this is how we calculate. First I evaluated for blue color one, length and width I got it from the figure, and then z value you can get it in the question. So simple m1, simple n value, and you can refer to the graph to evaluate I value and a value. So A is the delta sigma Z value. And then for you go for this orange color one. So for the orange color area, what you have is same length and same width. So even this one, right? Length and width, that is for this, right? So actually no need to once again calculate because the same thing is here. So even though you calculate once again, or else you calculate A into 2, right? Whatever it is fine. You can calculate once again for another step, or else you can multiply by 2 because these dimensions are same, L and B. L and B. So what happened then? M values are similar. Simple N values are similar. So that graph I values are similar. Surface pressure is similar, so that the final delta sigma Z value is similar. So no need to calculate B value. If you calculate A value, no need to go for another step. You can multiply by 2 and evaluate the combination of this one. Similarly, for the other one, this one, green color, 5, 1.5 Z value, and evaluate the delta sigma Z value multiplied by 2. No need to go for another step for this one because the dimensions are similar. Here, these two dimensions are similar. So that M values are similar. N values are similar. I values are similar. No need to calculate this step. You can, once you evaluate this one, you can multiply by 2. Right? So the point here, you have to think, okay, do we need to calculate this area? Because we additionally considered the similar area here. No need to deduct once again. This area can be compensated with this area, additionally considered area. Okay, like that you have to think. Okay, now, is that clear? Clear? Asha, and the
Yeah,
others?
sir, but
Clear, no?
the, දැන් මැද පාර්ට් එක දැන් ඩබල් වෙනවා සර් ඒක කමක් නැද්ද?
කොතනද?
අර සේම් සිමිලර් එකේ තියෙන සර් අර
මෙතනද
ආ
කියන්නේ?
හරි සර් හරි. අරක ඇඩ්
හරිද?
කරන්න නැති. ඔව් හරි. මේකට ඩබල්
මේක අපි
කරන්න.
ගත්තේ නෑනේ අපි ආශා. මේක
හරි.
ගත්තේ නෑ. හරිනේ? එතකොට මේ වගේම කෑල්ලක්නේ මෙතන තියෙන්නේ. ඒක
හරි.
නිසා තමයි අපි මෙතන ආයෙමත් ඇඩිෂනලි කන්සිඩර් කරන්නේ නැත්තේ. ඔයාට ඕන නම් මේක ඩිඩක්ට් කරලා ආයෙමත් අලුතෙන් මෙතන රෙක්ටැන්ගල් එකක් හිතලා මෙතන mn වැලියු අරගෙන එහෙම කරන්න පුළුවන්. නමුත් long procedure එකක්. No need to go
හරි.
that way.
හරි.
Okay, no? Okay. I hope the others also got the idea, right? So with that, we will move to the other session. That means we have now loading systems, right? So this kind of problems are also possible in your exam paper, right? So in your question paper, this kind of problems are also possible. What happens here? A loading system, a point load, two line loads, 2 or 3, and the area load is there. So kind of combination. So how to do? Like this, right? A point load is here. And dimensions to the point of consideration is given. Now point load is here. This is our desired point. So from there, we have to go down 3 meters. So accordingly, you have to evaluate what is the vertical stress increment due to this loading system. So there is a point load, a line load, another line load is there, and also an area load. So as a result of the combination of this loading system, what is the vertical stress increment at point A? That is what? to be evaluated, right? So how to do this kind of problem? Actually, we discussed about these kind of problems in our last lectures, right? So anyway, now I will remind you how to do this, right? So the bosonics theory, as I discussed with you last time, it has been evaluated for point loads, right? So the equation, so the developed equation is this one. So delta sigma z for any given point due to this point load will be this. So how to do that? The applied load, that is capital Q. So for considered depth, that is Z, and from here to here the horizontal distance, that would be R, and again Z. So these are the things you need to know: Q, Z, and R. If you know the Q value, if you know the Z value, if you know the R value, then you can evaluate the delta sigma Z value. Don't worry, these equations, right? අවශ්‍ය නම් මේ දේවල් ඔයගලන්ගේ question paper එකේ දෙනවා. Even the equations will be provided. No need to remember every of these equations, right? So now for the point load, you have to know the Q value, you have to know the R value, you have to know the Z value. So how to do that? So point load is 20 kilonewton, right? So Q value you know now. Q value is 20 kilonewton. Okay. And then we should know now Q value known, right? You know the Q value. Q value is okay. That is 20. What about this R value? R value is the horizontal distance to the point load for the desired point. What is the horizontal distance? This distance. How to do that? Now from here to here it is 6 meter. See, it is given here 6 meter. And from here to here it is 4 meter. So can you calculate the horizontal distance? That is possible, no? Square root of, using Pythagoras theory, 6 square plus 4 square. So that 36 into 16, 52, square root of 52. And 16. Okay, 52. So square root 52. Now this value, the horizontal distance is square root 52. So you just substitute the value here. R is square root 52. And Z value? 3 meters. The depth 3 meters. Here it is 3 meters. And here also 3 meters. Now you know all unknowns, so that you can evaluate the delta sigma Z value due to the point load. Very easy. Okay. Now, how about the line loads? Here we have 5 kilonewton per meter. Here we have 10 kilonewton per meter. So I discussed during our lecture. So in case of a line load, how to evaluate the point, the vertical stress increment at the given point, right? So that can be done from this equation, right? So Q into Z into IL. IL can be calculated from this equation. Okay. So once you calculate IL from this equation, you just apply here and substitute the correct value for Q and Z value so that delta sigma Z can be calculated. What is the requirement? You should know Q. Q is the applied line load. Z is the depth. So in order to evaluate the I value, you need to know X value. X is the horizontal distance from the line load to the point of consideration. You see, this is the X value. Okay. This is the X value, right? So that X value is the horizontal distance. And Z is the depth here. If you know the X value, if you know the Z value, you can evaluate the IZ value. Okay. For this line load, let's see. Q is 5. So the Q value is 5. The load is 5. And Z is 3 meter. Here Z is 3 meter. Here also Z is 3 meter. Right? And then you need to know the X value, the horizontal distance. What is the horizontal distance? Now from this is where the point load is. This is the point of interest. Right? So what is the horizontal distance? 4 plus 4. Totally 8. So X value is 8. As you know, phi is 3.142. Okay. So now every unknown is known, so that you can evaluate the vertical stress increment due to 5 kilonewtons per 5 kilonewtons per meter. So you can evaluate the same way. Now for 10 kilonewtons per meter, for that one also the difference is the same procedure. Difference is horizontal distance, that is 4 meter only. So that you can evaluate the vertical stress increment due to the line loads as well. Right? Now the balance is the area load. Right? So you have to evaluate for the area load. So when you see on the plan view, it is a rectangle. So very simple. Now you know how to do the rectangular loaded area. How to do? So this is the plan view of the same figure. So 4 meter, again 4 meter is the 10 meter, that is the total length. So this is the point of interest. How to evaluate? So you have to draw a rectangle having a cone of the area should coincide with this one. So how to do? First you draw a rectangle like this and deduct this by additionally considered rectangle. Very easy. So first you have to evaluate the simple m and simple n value for this one. What is simple m value? What is simple n value? You know that simple m is 8 divided by 3. 3 is the depth, right? Simple n is 10 divided by 3. And if you know the simple m and simple n value, you go to the graph and evaluate I value, right? If you know I value, you evaluate the delta sigma z value, right? So again, what you have to do, you have additionally considered this here. This is the point A. Actual loaded area is only a half of this. So this is only the loaded area. But this area you have additionally considered. So because of that, in this additional loaded area, you deduct. So how to deduct? You calculate for this one simple m and simple n. Again, you calculate for I value. And then you evaluate the delta sigma z value. Right? So deduct from this one delta sigma 1. This is delta sigma 2. So delta sigma 1 minus delta sigma 2 will be the final value. So what is the final total vertical stress? It is like this. You know the vertical stress increment due to the point load, right? So the point load delta sigma A, then line load 1, 5 kilonewtons per meter, that is sigma B, line load 2, sigma C, and area load, area load, we have sigma D. So the final total delta sigma D will be, delta sigma will be sigma A, the point load 1, plus sigma B, line load 1, and then sigma C, line load 2, plus sigma D, this area load. Okay. So this is how you evaluate for the loading system. Individually, you calculate for the stress increment due to the loading. First, you calculate for the point loads. Then you calculate for the line loads. Then go for the area load. And then evaluate the total sigma value. Okay. Is that clear? Clear?
Yeah, sir. So,
Clear.
අර question
Okay.
එක දාන්න පුළුවන්ද?
මොනවද?
මේ දැන් අපි හදපු question එක message එකේ දාන්න පුළුවන්ද?
Message එකේ?
අපි chat box
ඔයා
එකට
කියන්නේ
දාන්න.
present
නෑ
මේකද?
presentation දැන් question එක.
presentation එක upload කරන්න කියලාද කියන්නේ?
නෑ sir. දැන් හදපු question එක තියෙනවනේ sir. question එක.
ඔව්. ඔව්.
ඒක.
ඒක ඔයාට chat box එකේද ඕනේ?
ඔව්.
ඕගොල්ලන්ට screenshot එකක් ගහගන්න බැරිද ආශා?
ගහගත්තා sir. මේ question එකේ ගහගන්න බැරි වුණා.
right. Okay, okay. මේක නේද?
ඔව් sir.
right. screenshot එකක් ගහගන්න. Okay.
Yeah sir.
Okay.
sketch එක.
Right. Sorry?
sketch එක.
This one? Okay.
Okay.
Okay. Anyway, I will be uploading this presentation within today in the Moodle, including the last a couple of presentations. So you refer to the Moodle within today so that you can get this presentation within today, right? Okay. So this is another example, right? These kind of problems are also possible in your exam paper, right? I don't know from which area I'm going to make a question this time, but I will show you some of the examples in the past papers. So similar kind of questions can be expected in your exam paper, right? Following figure shows a pump room arrangement where the details are mentioned below. Pump room is made out of grade 30 concrete. The roof slab thickness is 150 millimeter. Thickness of side wall is 150 millimeter. And the height of the wall is 5 meter. Thickness of base slab is 200 millimeter. Base slab is extended 300 millimeter from the wall in either side. Length of top slab is 3 meter and width is 2 meter. At the center of the top slab, cylindrical type water tank is placed. For the calculation purposes, the load due to water tank can be taken as a dead load 3 kilonewton per meter, which is equally distributed. Calculated Calculate the vertical stress increment at point ABC below 3 meter from the stress certain level. Also calculate the vertical stress increment at 2 meter below the center of base slab. Actually, a lengthy question, right? I will show you a graph, right? A kind of sketch. So the water tank is there. This is a kind of a pump room, right? Water tank is located on the roof slab. And then what happened is there is a roof slab here. Two sides walls are there, and a base slab is here, right? You can see a base slab where it is extended beyond the wall, right? So I said it is 300 millimeter away from the wall, right? Either side, right? And then what happened here now? Um, there is a water tank. As a result, we say we can idealize that the water tank load as a dead load here. So that dead load, it is given in the question, and base slab dimensions are there, wall dimensions are there. It is made out of grade 30 concrete. So every information has been given. So what I am asking now, first you have to evaluate what are the loadings coming from this arrangement, and then as a result of those loads, what are the stress increments at point A here and B, C, and also at the center of the base slab, somewhere here. So kind of practical problem, right? Because every our structures as civil engineers, we are creating on the ground, so that these are the practical situations, right? So now let's calculate without taking much time. At the roof area, we have water tank. So it is given in the question that the load due to water tank is 3 kilonewton per square meter. It is given in the question. And load due to the water tank roof self weight, as you know, the concrete unit weight is 24, and the thickness of the water tank roof slab is given as 150 millimeter, so that the load coming from the water tank roof slab is 3.6 kilonewton per square meter. Okay. And total area load, it is given as it can be calculated as from the roof, it is 3 plus 3.6, it is 6.6 kilonewton per square meter. Okay. So load acting on the wall due to the above area load from the tributary area method. So you can evaluate the width of the roof slab is totally it is given as, let's go to the question. So it is given somewhere length of the roof slab is 3 meter and the width is 2 meter, right? Here this length is 3 meter, width is 2 meter. So that's why I calculated here 6.6 into 2, the total line load, and it is divided by 2 or multiplied by 0.5 because there are two walls supporting this roof slab. So that's why I have multiplied by 0.5. So the final value is again 6.6 kilonewtons per meter. This is the line load acting on the wall due to the water tank and the self weight of the water tank slab. Okay. And then finally, dead weight of the side wall also there. So it is 24, that is the unit weight of concrete into 5. 5 is the height of the wall and into the width. That would be 0.15, 18 kilonewton per meter. So total line load in one wall, it will be 24.6, addition of these two, right? So now line load, you know. So now here, the loads have been calculated up to here. The line load from here, you evaluated. Balance is this base slab area load. Up to here you have evaluated. So base slab 24, that is the unit weight of concrete. This is the thickness. So the area load is 4.8 kilonewton per meter. So what is this now? Area load plus there is one line load here and another line load here, right? So what you are asked to calculate is 2 meters away due to this loading system, what is the vertical stress increment at point A and point B somewhere here, point C somewhere here, and at the mid of this area, right? Okay. For line loads, very clear, right? The line load, you know, these are the equations, and Q value, it is, you have calculated. Q is 24.6 kilonewton per meter, this value. And then Z value, it is given in the question. And then X value, you can evaluate, because per line load, what is the distance, right? It is there. And then Z value, it is there. So for the two line loads, it is very easy. Similar like the previous example, I am not going to detail discuss on this one, right? So Q value you know, Z value you know, X value you know, Z value again you know. So because of that thing, you can evaluate the sigma Z value for both line loads, right? In the case of area load, right? So it is like this. For the center, it is very easy, right? You have to divide this base slab area into 4, the area. Again, that divided area, it is also a rectangle, so that you can evaluate simple M and N value for this small rectangle and multiply by 4, so that you can evaluate the vertical stress at this point at the center. In case of um, now, in case of area beyond, now there's another question. No, you have to evaluate for point A, B, and C. No, so what should be done by you? You have to consider an additional area, right? Right. So let's say this is only the loaded area. So you consider certain additional area like this for this point and deduct this area, additionally considered area. Likewise, I don't think it is very difficult for you, because we discussed about some of the complex problems than this in the previous situations. So the evaluation of area loads, I don't think it will be issue this time, right? So with that, we will move to this trapezoidal loads, right? So before that, we will have a short break, right? We will come back by, now it is 3:54. We will come back by 6:05, right? Sorry, 4:05. So with 10 minutes break, we will come back, right? Hello. I hope everybody is here. So we will continue. Now, we finish the rectangular loaded area, and last time we discussed about circular loaded area also. Now, we are moving to the trapezoidal loaded area, right? Trapezoidal loaded area. Now, in case of an embankment, in case of an earth dam, you consider the loading, the cross section of the embankment area, it will be like this. So this is actually here we will have a triangular area, and then we will be having a kind of the horizontal surface here, and this area we will be having a sloping triangular area. So the loading, this area will be a kind of a loading where a kind of linearly increased load will be here. A linearly increased load will be here. And then we will be having a UDL here, right? And then here we will be having a linearly decreased load. So the loading condition will be also a kind of trapezoidal shape. So this is not a rectangular load, or this is not a circular load, a kind of trapezoidal load. So in case of trapezoidal load, we we can evaluate the loading with certain kind of graph, right? So last time I showed you some graph. Today we are going to discuss a detailed example on trapezoidal load, because this is also a possible question in your exam paper, right? So never I have given a question on this area. So this time I can consider a question coming from this area, right? Okay. So listen carefully. What is the question? A highway embankment, as shown below, assume a average density of material in the embankment is 2 megagram per cubic meter. 2 megagram per cubic meter, right? Megagram is 2 into 10 to the power 6 grams per cubic meter. Okay. Otherwise, you can say 2 into 10 to the power 3 kilogram per cubic meter, right? So compute the vertical stress um, under the center line of depth 3 and 6 meter. Here, 3 meter from here to here, and again 6 meter from here to here at point A and point B, in other words. So you can see a triangle, a kind of trapezoidal embankment is here. So the unit average density of material is given also, and the dimensions are also given. So how to evaluate? First, I will refer to this graph, right? In the graph, what are the conditions? This is also, there are certain conditions similar as our rectangle situation, right? So what is the condition? First condition. So you see here, one graph is shown, a sketch or a diagram is shown on your right hand side bottom corner, right? You see here. There, what is this? A kind of trapezoidal load, but half area is given, right? So this is the complete trapezoid, but what we consider in this graph is half of the area. See, half of the cross-section area, right? So what is given here, you carefully see, right? Okay. This triangular part, the horizontal distance has been given as simple A. And this half area, this rectangular length has been given as B. So if you consider the total trapezoidal area, the horizontal area will be 2B, and triangular, another area will be there on the other side. Okay, understood? Now here, this triangular area, if you divided from this line at the center line, that will be considered here. So another portion will be there. Similar like this area will be on the other side, which is not considered here. Okay. So now this triangular portion, horizontal distance is simple A. Rectangle, this horizontal surface, the distance is B. Okay. And this loading here, it is gradually increased, and at the horizontal surface, it's become constant, becomes a UDA, right? So that loading is Q naught. Not here, it is at the constant region. The constant region, the unit load is Q naught. Okay. So at the below this point, under depth Z, the delta sigma Z value will be given from this graph. Okay. How to evaluate the delta sigma Z value? Delta sigma Z is equal to I into Q naught. Q naught is the load here. And I is the value obtained from this graph. So in order to obtain the value from this graph, what you have to consider is a point under the area, under the center of this area, center or at the horizontal position. Now, horizontal area is from here to here, no? From this area, you have to think about the point, okay? So, now what are these axes? Here, the horizontal axis is defined as A divided by Z. And there are certain curves. So, these curves will be given by B over Z. Now, from looking at this trapezoidal loaded area, B divided by Z can be calculated. A divided by Z can be calculated. So if you know the B divided by Z value and A divided by Z value, you get the point of intersection, go horizontally and evaluate the corresponding I value. So if you know the I value and if you know the Q naught value, you can evaluate the delta sigma Z value at this point. That's how you have to do. Okay. Now, referring to our problem. So, now this trapezoidal loaded area. So, in order to apply to the graph, we have to divide our area somewhere here. So, if we divide here, we can evaluate the load at this point, right? And multiply by 2 because the same area will be repeated here so that we can evaluate this point what is the vertical stress. If you want to evaluate the stress, similar procedure can be followed. Okay, let's see now. Let's calculate the applied surface stress Q naught and the dimensions of the embankment in terms of A and B. From the figure, B is equal to 5 meter. See, 5 meter, right? Totally it is 10 meter, but our point of interest will be somewhere here. So the horizontal portion will be only 5 meter. So what is meant by B? B is the horizontal length. So horizontal length in this situation, it is 5 meter. And A will be simple A, means this triangular part. So how to evaluate? Now you can see the slope. So as per that slope, if you go 1 vertically, horizontal slope is 2. So if you go 3 meters, means the length, the horizontal distance is 6 meter. Understood? The slope is 1 to 2, no? So the vertical height here in the triangular portion is 3 meter. So that means the horizontal distance is 6 meter here. Okay. So that's why 2 into 3 meter, A becomes 6 meter now. Now let's calculate the vertical stress for Z is equal to 3 meter. Now, what you have to do as per this graph, you have to evaluate A over Z and B over Z. Let's calculate. A over Z is 6 divided by Z is 3 meters. 6 divided by 3, that is 2. B over Z, 5 divided by 3, 1.67. Now, you calculate the Q naught as well. What is Q naught? The load coming from the soil weight. As you know, the soil material, the density is 2 megagram per cubic meter. So in order to convert this one to the Newton, what you have to do is you have to multiply by 9.81. Then it becomes Newtons, right? And then rho GH, H is the height. Here the height is 3 meter. So what is height? 3 meter. So the Q naught value will be 59 kilopascal, right? I think up to this point, it is clear to you. If you have any question, please let me know. Ranmini, Asha, Asiri, is there any problem? Samarajiva,
No, sir, please.
Asha, clear, no? Okay. Now, from this point onwards, it is very easy. AO Z is 2, BO Z is 1.67. You go to the graph. AO Z is 2. Now, where is 2? It is somewhere here. So, 2 is here. You go down. And then BOZ is 1.67. 1.67 is somewhere here. Right? This is 2. This is 1.6. So somewhere here. So you go horizontally until you find the corresponding I value. Okay. So corresponding I value is 0.49 from the graph. 0.49. Okay. So the vertical stress development is Q naught. From the previous slide, you calculated it is 59. 59 into 0.488. 49 or 488 or the closer value. So the value will be 29 kilopascal. Means surface pressure is 59. Surface pressure from the embankment is 59. But when you go down 3 meters, the pressure becomes 29. Okay. So 1/2 of the embankment is this. But because you have considered only the half, if you want to consider for the other half, this value should be multiplied by 2. So the final value is 58 kilopascal at 3 meters depth. So you see, there's nothing much difference from the surface pressure when you go down 3 meters. Even you go 3 meters down, only 1 kilopascal has been reduced. Okay, so that's why I mentioned, thus at this shallow depth, this delta PZ is the vertical stress increment is almost same as the contact stress. Contact stress is 59. Here you can see 58 at 3 meter. Nothing much different. Okay. But when you go down 6 meters, the problem will be different. You can see AOZ value now becomes different, right? Previously AOZ 6 over 3. Now it is become 6 over 6 because depth is 6 meter. Similarly, for BOVZ value can be calculated. So from the graph, you refer as previous, I value can be calculated as 0.44. So when you go for the final value, 59 into 0.44, because there are two trapezoids equivalent, you have to multiply by 2. The final value is 52, right? So you can see even at the 6 meters down, the value will be much closer to the contact pressure, right? So, hope you understood this trapezoidal load case, right? So, what we have done, we have considered a point at the center. That's why we have multiplied by 2. But if in case we considered some other point, right? So this is the case we discuss, point A. In case of point A, right? Very clear. You can calculate this for this part and multiply by 2, right? If it is equal. But if in case, right, this is the, let's say this is your trapezoidal area. Your point of consideration is somewhere here, which is not at the center. So in this situation, you cannot multiply by 2, but you know B value for this one. So that B over Z value can be calculated. A over Z value can be calculated. And you can evaluate the I value, right? And then you can evaluate the delta sigma value, right? Here also, you can evaluate B value for this one, another B value, not this same value. And the A value also you can calculate. So A over Z and B over Z can be calculated. For this small trapezoid also, you can evaluate the I value and delta sigma Z value. And then add together. That is possible, right? But if you want to have a kind of point B, what is the situation? Huh? What is the situation? So in this situation, for point B, you consider a trapezoid like this. So that A value, B value, A over Z value, B over Z value, and then I value can be calculated. That is easy. And you have to deduct this additionally considered triangle, and again you have this particular small triangle also, you have to add that part. Okay, clear? Now you may worry how to evaluate for triangles, right? How to evaluate for triangles. It is like this. So these are the triangle loadings. You can see a triangle loading is there. So the triangle horizontal length is capital B. The load, triangle maximum load is Q naught here. And the length is here, length L. So capital M and simple M and simple N should be evaluated. Simple M will be capital L divided by Z. Simple N will be capital B divided by Z. Okay. So in this situation, for the triangle, you can evaluate the L over Z, you can evaluate the B over Z, and then the vertical stress increment will be I into Q naught. Q naught is the maximum load here at the triangular loading, the maximum loading. Okay, Q naught. So how to evaluate I value then? If you know the M and N value, you can evaluate the I value. How to do? Now, in this horizontal axis, the value of M is given, simple M. And these curved lines, value of simple N is given. So, if you know the M value, if you know the N value, so similar as previous, you can evaluate the I value. So by doing so, you can evaluate the triangle loading for this case. In case of point C, what will happen? So triangle loaded area, trapezoidal loaded area is somewhere here. Now we are considering point beyond the triangular loaded area. Sorry, beyond the trapezoidal loaded area. So in this situation, you have to do like this. How to do? Now our beyond position will be somewhere here. So we consider our trapezoidal up to here. Up to here we consider, right? So that means we have additionally considered this area, which is also a trapezoid. So that trapezoid we can separately evaluate, and that impact we can deduct. So deduction will be applicable. Okay. Hope you understood. Clear? Right? Asha, clear? Is it clear?
Yes, sir.
Okay. Asiri, Udeshika, Samarajiva, clear? Hmm? I don't know whether it is clear to you. So if you have any question, please let me know. If you don't have any question, we will proceed. Asiri, do I need to discuss this part again, or is it okay? Udeshika. තේරුණාදු දේශිකා අසිරි සමරජීව. I don't know whether you are in the class. Anyway, I hope it is clear to you. So what I mentioned here, we discuss about point A, right? And then we discuss about point B, which is not similar to point A. We discuss in detail regarding point A, but for point B, I discuss you the method, right? So here, if you consider point B, it is not coincide. It is not in line with the graph condition. Graph condition, it should be horizontal when the point is considered. The loading area should be horizontal. But in this situation at point B, the loading area is not horizontal at the point of consideration. So at the point of consideration, this loading area is not horizontal. So it is a kind of triangle, right? So because of that reason, we have to consider a red color triangle area additionally to make the graph condition, and then this area we will deduct from this area, and then yellow color area we will additionally consider, right? For point number C, it is not at all in line with the graph condition. So we make that situation into the graph condition, where we additionally considered certain area in red color. So that lies with the graph condition, and this additionally considered area we will deduct, right? It is also a trapezoidal area. Okay, right. So with that, I have a question here. An embankment is shown in figure 9.12. It is this one. Determine the stress increase under the embankment at point A1 and A2. Right? A2 is here. A1 is here. So what you have been asked was, so as a result of this loading, right, you have to evaluate what is the vertical stress increment at point A1 and A2. So here, this is the bottom of the embankment. So you have to consider 5 meter down. Here also 5 meter down. So you go for the graph which we discussed short while ago and evaluate for this one, right? So I will be uploading this presentation today in your LMS. So please refer to that one, and then we will discuss this these question if you have any doubts in the next class, right? So with that, we will be now moving into today the balance part of the session, right? Okay. So I'm having a short uh, session with you. That session I'll try to complete within today. I don't want to complete the full presentation, but I need to complete this Westergaard's theory with you, right? So this Westergaard theory, actually this one, it is more or less equal to the Bosonics theory. Same assumptions, but this theory has been developed for kind of practical situations. Practical situation means, hope you can remember, in the bosonic theory, we have considered several assumptions, right? The soil is homogeneous, soil is elastic, soil is isotropic. Likewise, we have considered many assumptions, right? But such kind of situations are not available in practical situations. So you can see many layered soil. So it is not a homogeneous soil in practical situation, right? So whatever the decisions coming from the bosonic theory may not be fully applicable for practical situation. So to evaluate this situation, Westergaard has developed his own theory to evaluate the vertical stress increment under given point. Now we are going to check that theory under your course. Okay, right? So now we discuss about the approximate method. Orally we completed, right? So we discuss about the bosonic theory that is already completed. Now we come to this Westergaard method, right? Okay. The reason, as I said, bosonic theory derived for homogeneous, isotropic, linearly elastic half space. But many natural soils sedimentary in nature, right? Like layered. So this homogeneous situation is not available in practical situations. Most of the soils available in the world are not homogeneous because those are in layered manner. So Westergaard theory considered infinitely thin elastic layers of soil. So we do not consider this as homogeneous. We consider there are layered soil, right? But we consider linearly elastic nature. Understood? Westergaard considered the elastic principle as it is, but he has changed from the bosonic theory this homogeneous property, which is highlighted and I underline here. That property he understand it is not naturally available. It is we have a layered soil. So because of that thing, that property, he has changed in his theory as a layered soil. Okay. So remember those things in 3-mark questions, 2-mark questions, those kind of questions can be available. So I may ask, why Westergaard theory? Uh, what is the difference between bosonic theory and Westergaard theory? What in assumptions? What they have assumed differently than the bosonic theory? Something like that I can ask. So you need to understand those principles well. Okay, right? So the Westergaard theory for point load, we will consider the point loads only. So in that situation, so this is the equation developed by Westergaard, right? So you can see the mu, the Poisson's ratio of the material has been considered and it is incorporated in the equation. So the Westergaard, now he has incorporated the layered nature. Each layer, there is mu factor. Mu means the Poisson's ratio. So the Poisson's ratio will be governed in this equation. Everywhere it is available with mu value. But for our comparison purposes, we will consider this mu value as 0. If the mu value is 0, what will happen? If you substitute the value mu as 0 In that situation, this equation can be simplified to this equation. Okay. So when you substitute 0 for this mu value, this equation will become this equation. Right? So if you can remember, the bosonics theory also had this kind of equation. Right? So it is more or less similar. So we will compare these two values with this arrangement. Okay. So these two equations, Westergaard equation and bosonics equation, we will compare with each other, right? By comparing the values coming from this simplified equation. So what I did was, I summarized this equation and I applied mu as 0 and make the equation as this, where IW is equal to this value. We simplified. Okay. So hope you can remember, in bosonics theory, we had IB value. And here we have IW value. So this IW value, since the mu value has been taken as 0, now here IW value is independent of all material properties. No material property is there. R is the horizontal distance. And then Z is the depth. No other property is governed by the material properties. Right? So this can be compared with the IB value which is given in the Boson equation. Right? So this is the IW value. This is IB value. IW is the shape function from Westergaard theory. IB is the shape function from bosonics theory. So you can see what is the difference, right? Here we have 2, but here we don't have 2. Here we have a factor 1. Here we have a factor 3 divided by 2. Here we have a power 3 divided by 2. Here we have a power 5 divided by 2. Right? So you can see how it is different. Right? So now let's assume R divided by Z, this value as 0. In case R divided by Z 0, what will happen? So this part entirely it becomes 1. This part entirely it becomes 1. So here IW will be 1 divided by 5. Here IB will be 3 divided by 2, 5. So if you represent the values like that in a graph like this, where x-axis is IB or IW, y-axis is ROZ. If ROZ value is 0, IW will be somewhere here and IB will be somewhere here. Like that, if you plot the variation of IB and IW against RZ value, that will be this variation. So, by referring to this graph, what you can see, that would be the question. Okay. What is this IB and IW? First, we have to go for that one. IW is this one. If this IW value is increased, sigma Z value will be increased. If this IW value is decreased, sigma Z value will be decreased. So having that idea in your mind, now here compared to IW, IB value is always greater. So that means if you use the bosonic theory, the bosonic solutions will give you a safer value compared to Westergaard theory. You see, it always gives the higher value. It always gives the higher value for shallow depth, lower depth. But if you go to the higher depths, what will happen? The two values will coincide with each other. It is more or less similar, right? So IB and IW becomes more or less similar, and finally it will closer to 0, right? Okay, right. With that understanding, we will now proceed. So we have Westergaard theory, we have Bosonics theory. So compared to the Westergaard theory, the Bosonic theory is giving you a conservative result. So that can be identified by this graph. There in this graph, we have two values, IW and IB. So IB always give the higher value for shallow depths, but IW is giving the lesser value. So compared to IW, IB values are better and safer and more conservative. Okay, right? So if somebody asks you, what is the theory you used for Bosonic theory or Westergaard theory? You have to explain. For shallow depths, Westergaard theory will give you less conservative values, but Bosonic theory will give you a conservative result. So I will select Bosonic theory for shallow depth. But when you go to deeper situations, the values will be coinciding with each other for two Westergaard and Bosonic theories, right? So the value will not be much different. Whatever theories can be used. So likewise, you have to give the answer, right? Okay. Hope you understand. If there is any problem, please let me know. තේරුණාද? ළමයි තේරුණාද?
Yes, sir.
Okay. Right. Now, similar like Bosonics theory, for Westergaard theory also, similar graph have been drafted, right? Similar charts have been developed. So similar like Bosonic theory, we have L and B value and Z value. Same like Bosonic theory, the loaded area, one of the corners should be coinciding with the corner of the desired point, right? So simple M value can be calculated by B over Z. Simple N value can be calculated by L over Z, right? So if you know the B over Z and L over Z value, here you can see that is simple N here, and this curve graph will be simple M. So if you know the simple N value and simple M value, you can get the point of intersection and go horizontally until you find the corresponding I value. So if you know the I value, you have to multiply by Q, that is the surface stress contact pressure. That will give you the sigma Z value. So as I said you, so similar charts are available, but the values are different, right? The results you get from Westergaard chart and the Bosonic chart are two different, but the same principle, same arrangement, same way of reading the charts, right? So if you know the Bosonic theory charts, you can go for Westergaard theory without any issue, right? So these are the graph, but you have to always think the Poisson's ratio has been taken as 0 in developing this chart, right? So that's what I mentioned here. The influence values for vertical stress under corners. The corners are the speciality, right, of uniformly loaded rectangular area for Westergaard theory. Always you have to remember that these charts have been developed for the corner cases for rectangular loads. So when you think about the rectangular loads, if your point of interest is not coinciding a corner of the rectangle, then you cannot use this graph. So that what you have to do is you have to divide your rectangles, add certain rectangles, and then make a common corner at the desired point so that you can use the graph. Okay. So similarly, there are several other comparisons, right? So you can see in this chart, in this table, the influence values for vertical stress under center of a square uniformly loaded area. Square footing, let's say square footing. So in that situation, the Poisson's ratio is 0. So you can see square loaded area is there. One side is given as simple A. So I naught value, right? For the center condition, right? We are going to check the influence values for center. So I naught value has been given for bosonic theory and Westergaard theory. So A over Z value from infinity to 0, it has been varied. So when you consider the bosonic value and Westergaard value, always the bosonic values are high. You can see, always bosonic values are high. So if you use the bosonic value and evaluate the I value, the influence value, what will happen? You will get the higher loads, right? You will get the higher loads compared to the Westergaard. So let's say you have 100 kilonewtons per square meter as contact pressure, and you are going to evaluate the stress at 5 meter down. So right, 100 kilonewtons square loading will be there, 100 kilonewtons per square meter, and you are going to consider 5 meter down. So you have two theories, bosonic theory and Westergaard theory, right? So if you check the vertical stress increment due to 100 kilonewtons per square meter square loading from the bosonic theory, so you will be receiving higher value at this point compared to the Westergaard theory, because influence values are higher, always higher compared to Westergaard theory. So that's why I say the bosonic theory will give you a safer value. So if you have higher loading here as the calculation, then you will think of some improvement method, right? You will think of some arrangement of uh, stress distribution, some other arrangement of stress distribution. Let's say there's a clay layer at 5 meter down. In that situation, if you have considerable higher load there, right? When you check the distributed load, the load at the clay layer is higher. In that situation, the consolidation settlement can be expected, right? So those things you can make some pre-arrangement if you use the bosonic theory. So it will give you more conservative result, more safer results. Okay. So in your module, we will be discussing about this consolidation as well. There, I will combine this theory, right? The vertical stress distribution, this theory and the consolidation together so that you can understand, right? So I will be අපි කතා කරනවා ක්ලේලේ එකක් තියෙනවා පොළවේ අභ්‍යන්තරේ ක්ලේලේ එකට මෙහෙම අපි පස් කන්දක් උඩ ගහනවා එතකොට මේ පස් කන්ද උඩ ගැහුවාම මේකෙන් එන ස්ට්‍රෙස් එක මෙච්චරයි contact stress එක. ඒකට මම අහනවා ක්ලේලේ එකේදී මේකේ stress distribution එක කොච්චරද vertical stress increment එක. ඒත් මම අහනවා ඒ vertical stress increment එකේ හින්දා මේ කොච්චර settlement එකක් අපි බලාපොරොත්තු වෙනවද. ඊට පස්සේ 90ක් consolidate වෙන්න කොච්චර කාලයක් යයිද. අන්න ඒ විදිහට අපි ප්‍රශ්න combine කරන්න පුළුවන්. Right? Okay. So my point here, the bosonic theory, if you use the higher values, always you will get. Okay, right. So this is in case of strip foundation, right? Long strip footing, in that situation, the length is too much high compared to the width. Length is high compared to the width. For example, retaining wall foundation, boundary wall foundation, like that, right? So in that situation, the values will be always higher in bosonic situation compared to the Westergaard. The influence values coming from the bosonic theory will be higher compared to the Westergaard theory. Okay. So the values will be more safer in bosonic theory. Okay. Right. So this is in case of uniformly loaded rectangular loaded area. So the influence value you can see here, right? So here LOVZ and BOVZ, the same LOVZ and BOVZ we consider for Westergaard theory and bosonic case. So when you consider the bosonic case, LOVZ is 0.8, BOVZ is 0.1. So in this situation, you can see the influence value coming from bosonic theory is 0.026. If you use the Westergaard theory for same situation, the value will be 0.17, 0.017. So the value will be higher in bosonic case. So the influence value is high means the vertical stress value is high. So you will be having a conservative result for bosonic case for rectangular loaded area as well. Okay. So the summary. So we have been discussing for approximate loading method, bosonic theory, and Westergaard theory. So here, bosonic theory, we discuss IB value. The difference between the bosonic method and Westergaard method is IB and IW value. So IB value will be given by this part, this equation. IW value will be given by this equation. So we compared and we found that Westergaard values are always lesser than Bosonic's value. So it's better if you use the Bosonic theory compared to the Westergaard theory. So the difference between the Bosonic theory and the Westergaard theory is we compared the actual situations. So bosonic theory, we say homogeneous soils. Westergaard method, we consider the layered soil. And then to compare these two equations, we assume the mu as 0 in Westergaard method. Okay. When we compare this method, we always observe IW will give you a lesser value. Okay. Hope you understood. Is there any problem up to now? Because we are going to conclude the session for today, right? So we discussed today some of the key examples for bosonic theory. And then we discussed about Westergaard theory, right? Under the bosonic theory, we discussed today regarding rectangular loaded area, irregular shape, but which can be derived as rectangular loaded area. And then we discuss about some of the loading systems and practical situations where point loads, line loads, and area loads are combined. And then finally, we discuss about trapezoidal loads and triangular loads, right? Then at the last part of the lecture today, we discuss about Westergaard theory, and I explain you why we are using Westergaard theory, what's the main reason, what's the main difference between bosonic theory and Westergaard theory. And for the comparison purposes, we assume mu as 0 in Westergaard theory. And then we found that uh, bosonic theory will have more conservative results than Westergaard theory. So those were the things we discussed today. So if you have any problems, please let me know. If not, we will wind up the session. මොකෝ කියන්නේ? ප්‍රශ්න තියෙනවද? ආසිරි, ආශා, සමරජීව, උදේශිකා. ආසිරි, is it clear?
Sir, clear, sir.
Okay, Asha,
Yes, sir.
Deshika.
Then,
Asha, clear, no? I didn't get you.
yeah, sir.
Okay, right, good. Udeshika, Samarajiva, I hope you two are also fine, right? So next week, we are going to discuss about pressure isobars, right? So we will be discussing about this theory, right? Right. With that, we will wind up today. And next week, we will be discussing about very important topics. We will be completing our most of the theories for pressure isobars in the first session. The second session, we will be discussing about shear strength, and the Mohr circles, the failure envelopes. Those things will be discussed in the next session. Okay. So with that, we will wind up the session. Thanks for joining. So
Thank you.
some of you have cooperated to me. Thankful to everybody. Okay, we will meet next Saturday, 2 p.m. Thank you so much.
Thank you, sir.
Thank you, sir.